Welcome back. Let's pick up where we left off. To calculate population stability index for a single feature, we need the proportions of observations by category for all its dummy variable categories. We can calculate that easily for each original independent variable and for the categories of credit score. But how can we do it simultaneously for all variables? Well, by taking advantage of how our data is organized. Let's take the inputs with reference categories with intercept data frame, for example. We know that each dummy variable has a value of 1 if an observation is part of the respective category and a value of 0 if it isn't. Also, each observation is part of one category only, so if it has a value of 1 for one dummy variable, the values for all other dummy variables are zeros. So, summing by columns gives us the number of observations of each original independent variable category. But we needed proportions, right? Well, we can easily get them by dividing each of these numbers by the total number of observations, or rows, of the data frame. In other words, we can divide the first element of the shape of the data frame. Great! Now we have the necessary proportions stored in the PSI calculation train variable. Let's repeat those steps for the new data and store the results in the PSI calculation 2015 variable. Awesome! It's time to concatenate the two sets of results into one data frame. Lucky for us, the PD concat method connects the two series by dummy variable name. Since these names serve as a row index, now the two sets of results will be perfectly matched. After this operation, we won't need the variable names to be row indexes anymore. So let's reset the index of the PSI calculation data frame. Since the names of the dummy variables were indexes, our last statement created a new column in the data frame called index, which now contains them. Alright, we saw that in order to calculate PSI for an original feature, we need to sum the contributions of each categorical dummy variable that belongs to this feature. It will be easy to do this if we have the original feature names in a separate column here. Let's take advantage of the fact that the names of the dummy variables are composed by the name of the original feature and the name of the respective category, separated by a colon. We can take it easily by using the split method. First, we take the index column and apply string split and indicate colon as a separator. We also specify we want to return the left part of the split string. To indicate that, we place 0 as an index here. After running the code, the last column of the data frame will contain the name of the original independent variable. Okay. Now let's change the column names to index, proportions train, proportions new, and original feature name so we can understand them more easily. We can also reorder them so we can also see them better. That's pretty simple. We will put index and original feature name in the beginning, followed by proportions train and proportions new. Awesome! This data frame is actually a result of two data frames. We had to calculate scores in order to come up with categorical dummy variables for score intervals. However, when we aggregated and calculated proportions, we were left with two redundant rows here. See? We don't need the intercept and score for PSI calculation. So let's overwrite the data frame for calculating PSI with the same data frame that contains all rows except for the intercept and score in the index column. Good. We have everything we need to calculate the population stability index for all original features at once. Population stability index equals the sum across all categories of a feature of the difference between the proportion of the cases in the original, the population for a category, and the proportion of the cases in the expected population for a category, multiplied by the logarithm of the ratio of the two. Let's split this into steps. So, first, we calculate the difference between proportions new and proportions train for each row in our data frame. Second, we can multiply that straight away by the logarithm of the ratio of their proportions. Let's calculate these contributions of the dummy variable categories in a new column called contribution. Now, that alone would be sufficient to calculate the contributions of the dummy variable categories to the PSI of an original feature. However, any of these proportions can be 0. So what happens if either the actual or expected proportion is 0? If this is the case, we will have numerical stability issues. So whenever it happens, we will just set the contribution of a dummy variable to be 0. Let's override contribution by setting its value to 0 if either of the proportions is equal to 0 and to the PSI calculation otherwise. Good job! The only thing left to do is to sum the contributions by original features. It's really easy. We can do it simultaneously for all features by grouping the PSI calculation data frame by original feature name, taking the contribution column and applying the sum method to it. That's it! What we get is a table with the population stability indexes of all original features. Great work! But those numbers mean nothing without being interpreted. We said that values lower than 0.1 indicate minor differences between populations. Values between 0.1 and 0.25 show moderate differences where some explanation and actions for model calibration may be needed, and values above 0.25 reveal major differences that require immediate attention and recalibration of the model. Let's start with the original independent variables. So all features here except for score. Starting from accounts now delinquent through address state, through annual income, all the way to home ownership, the values of population stability indexes are less than 0.1. You can notice that debt to income has a population stability index of almost 0.08. Still, that is below 0.1, so there are only minor differences between the original population that the PD model was trained on and the population of new borrowers with respect to any of these features. The first feature that is definitely problematic is initial list status. The population stability index for this feature is greater than 0.33. This is way higher than 0.25, right? That means the population of new applicants differs substantially from the original population. Let's look at the proportions of borrowers falling into the different categories of initial list status to check if we're right. We can see that in the population used for model building, there are about 35% in the W category, referring to whole loans, and about 65% in the F category, or fractional share loans. In the new population, there are about 63% in the W category and about 37% in the F category. It is worth noting that these refer to the strategy of the bank rather than the characteristics of the borrowers. All right. What about the other PSIs? The population stability indexes of the last three variables, inquiries in the last 6 months, interest rate, and months since earliest credit line are also below 0.1, so there are no concerns there. The PSI of months since issue date, however, is 0.3, so much higher than 0.25. Therefore, the two populations differ considerably with respect to months since issue date. Let's think for a moment what this variable reflects. It shows the number of months since the loan was issued. The new population consists only of loans granted in 2015, so it's natural that their time since issue date is lower. What causes this difference? Well, it depends to a large extent on our calculation, and not so much on the differences between the two populations. Therefore, this difference would require additional investigation. Population stability indexes for all remaining original independent variables are also pretty low, so there are no concerns there. Now, let's roll up our sleeves and interpret how the two populations are distributed with respect to the dependent variable, or the estimated probability of non-default. Score reflects just that. Its population stability index of score is 0.3, definitely greater than 0.25. So, we can conclude there is a huge difference between the two populations with respect to the outcomes obtained by the model. To summarize, The new population differs from the original population by 2 of the 17 original independent variables and the outcome of the PD model. For both independent variables, the differences may not be due to a change in the characteristics for the borrowers themselves, though. Even if we decide to change the model based only on this information, we can expect a considerable change in the coefficients of these two features, but not the rest. That said, we also found that the populations differ with respect to the estimated credit scores. This is the most serious population change that we can observe, as it implies our model outputs are considerably different than those before. That's a serious concern and a great indication that we must train the whole model again by including the new population in the training dataset. Thanks for watching.